Okay, well, thank you everybody who's joining in tonight. My name is Jackie Kra, and the title of this presentation is The Future of Miami, Florida, Flood Risk Modeling for Sea Level Rise. The question that I set out to answer with this project was, how is sea level rise going to impact Miami's more critical infrastructures, such as their hospitals and schools, and then their socioeconomic populations like age and income groups? And the reason that I wanted to focus on Miami in particular is because it's not only one of the more economically vulnerable cities in the United States, but there are some flood risks that Miami faces that are somewhat unique to the region. So I'll go over some of those. Sea level rise itself is projected to continue to increase at a higher rate than the global average. Also, it's flat terrain, low elevation, don't allow for much wiggle room. So just a couple extra inches of flooding can really make a huge difference in the damage. And then this region has experienced storm surge walls that are upwards of 15 feet. And the main flood risk that really grabbed my attention in wanting to do this project on Miami are its king tides. So king tides are just regular diurnal tides, but this is kind of a new phenomenon for Miami. It used to be that they would just be referred to as king tides in other parts of the world, but it's a new problem for Miami because of sea level rise. And their drainage systems haven't been able to really protect from them. Also, coastal subsidence and saltwater intrusion are kind of in a positive feedback loop with sea level rise. And lastly, the Gulf Stream weakening has not allowed for coastal waters to be adequately pulled offshore. So it's for all of these reasons I wanted to create a flood impact prediction model for Miami, and to do this for the year 2040. So an outline for tonight, I would like to help you become familiar with the study area, and I'll discuss why I chose to focus on the particular flood levels that I did. And I'll run through my methods, and I have plenty of visuals to show you for the results and the conclusion. And then we can briefly touch on data sources and references. If you're not familiar with southeastern Florida or Miami-Dade County, please take a look at the inset map of Florida. In the right-hand side of this map, you can see Miami-Dade County highlighted. And then Miami-Dade County is shown with a small study area highlighted within that. I didn't want to just include Miami city limits. I also wanted to include some of the surrounding neighborhoods, such as Miami Beach and the other barrier islands, because of course they're going to be more susceptible to flooding. Also just notice the two rivers on the western portion of the study area, and also the interstate, which we'll see in a moment is much more highly elevated. Okay, here's an elevation map for you to become familiar with the topography. This is rather monochromatic, dark gray, telling us that a lot of the study area is at or below sea level, especially Miami Beach. And the only areas that are really going up to that 15-meter level is the highway. So I'd like to talk about how I determined the flood thresholds. So first I wanted to decide what's going to be the sea level rise for the year 2040. The Intergovernmental Panel for Climate Change does have a projection for this year that for southeastern Florida, if we were to continue under a moderate to high carbon emissions scenario, we could see 8 to 13 inches. So for simplicity's sake, converting the data from meters to feet, I decided to use 12 inches of sea level rise for this year, and then to add it to 3 main flood events. So the The first one is kind of the lightest flood event. That would be kind of an average heavy rainfall event. So taking climate data from the past 30 years, the average of the maximum annual rainfall is about 5 inches. So adding that sea level rise to that, we're going to be looking at 1.5 feet. And the second event is kind of a high watermark flood. So that's just a term that means it's on the higher end of what they typically expect in that region. And currently for Miami, it's 3 feet. So we're going to look at a 4-foot flood. And then I also wanted to account for a storm surge wall. So I looked at increments of 6 inches all the way up to 20 feet. In the past, 1992, actually, Hurricane Andrew had hit Miami with a 17-foot storm surge wall. All right, let's just jump into the methods used for determining the impacts to the critical infrastructure. Okay, so I was looking at hospitals, schools, fire, and police stations, and the goal was to create binary maps showing flood and non-flood bins for each of those flood thresholds that I just went over. And so here's an example of a 4-foot flood with the flood bins showing where you're seeing blue is indicating the flooding. And so to create these, I took a national elevation data set, digital elevation model, and then in Esri ArcPro ran a flow direction tool on it to check for and then fill any sinks in the data. And once I was sure that it was free of sinks and seamless, I ran a calculation on it that said wherever the surface is less than or equal to one of those heights, then it would give an output such as this example. And then from there, I would just count the structures at every level where they touch the boundary of those flood bins. Okay, the next method was to look at the impacts to the socioeconomic groups. So this was going to involve a hotspot analysis with comparing that to a flood hazard zonation. The criteria that I used was elevation, hurricane wind speeds, and precipitation. And I used a weighted ranking system to create the flood zones. So for elevation, I calculated the mean elevation on the census tract level, broke those into 5 classes, and then ranked them accordingly. And then for the hurricanes, this was based on wind speed because that's what causes the storm surge. So I took 50 years of hurricane points and then created an interpolated surface of those with a spline method. And then wherever those fell within each tract, they were assigned, the tracts were assigned a weight for that. And then precipitation, same thing. If the tracts were near one of the 3 rain gauges used, then they were classified with a weight value. Here's a sample of the census tract attribute table that I used for this. So you can see that elevation, hurricanes, and precipitation have a weight here, and then that was added up into a total hazard field, which was then used to create the flood zones. And here's a map of those zones. The extreme high risk showing where the rivers exist, and the lower risk is a little bit more inland. Okay, so moving into the results. With the average heavy rainfall event, there was no flood inundation to any of these buildings. However, at the current high water mark of 3 feet, there is 1 fire station that could be impacted by this kind of flood. In contrast to that, for the year 2040, we're seeing possibly 3 fire stations, 1 hospital, and 4 schools that could be affected. And here's a graph showing you the overall trend of newly impacted buildings with each 6-inch increment of flooding. And I think it's a pretty steep trend. What I noticed is that the hospitals and fire stations were overall kind of unscathed. The police stations kind of existed in networks, so they were affected pretty swiftly at one level of flooding. And then I made this animation just to show you spatially how they're being affected. Miami Beach is gone pretty quickly. And this is going up to 20 feet. You can see that by the interstate, if the schools happen to be there, they're safe for quite a while. Then moving on to the hotspot analysis for the socioeconomic impacts. The map on the left is showing you overall household median income. The yellow is highlighting the extreme risk zones, and where that overlaps the hotspot for the higher income groups. In red, you're seeing orange. So I found that the higher income groups were more affected in the Biscayne Bay Islands and along the coast of downtown Miami. The more noticeable of the results, or that were striking to me, was the age group 45 to 64. So it looks about the same as the overall income, but this was actually, this group had the most area that was affected by or that was in the extreme or high risk zones. So in conclusion, I would say if we were to assume 12 inches of flooding by 2040, there will be 7 times as many of what we're considering infrastructure critical to a functioning society would be underwater with a high watermark flood. The income group aged 45 to 64 were disproportionately found in Biscayne Bay Islands and downtown Miami, where they existed in the higher risk for flooding zones. And so further studies, I would definitely account for the drainage systems here. And I think that this could be built upon using property value data and possibly revenue generated from tourism or retirement to add that into the economic study for the age groups. And I think we can open it up for questions.